Okay, so now we've done a couple of examples with some calculations. And when we did that, we hopefully noticed that it took us a lot of time to write out by hand statements like this. What does the output get closer to as x gets closer to 1? Or or as x gets closer to 1, the function g of x gets closer to -4. So in mathematics, we like to shorthand everything. And this is the concept of the limit. As x gets closer to 1, we found that g of x got closer to -4. So how are we going to write that in shorthand? Well, we're going to write that as limit. And here's how we do it. We say LIM x arrow 1. So notice how the x arrow 1 is underneath the LIM. And then we say of g of x. Or if you'd rather, it turns out you can write it LIM x arrow 1. And instead of g of x, you can just replace that with the expression that g of x represents, the 3x minus 7. So that's the shorthand for saying we want to find what the output is as the input gets closer to 1. So we want to find what the output is as the input gets closer to 1. And the way we say that, the way we phrase that in mathematics is we say the limit of g of x as x goes to 1, or as x gets closer to 1. Now, we know in this example that happened to be -4. So we could say the limit of g of x as x goes to 1 is -4. And the way we would write that is LIM g of x gets closer to 1 equals -4. Or LIM 3x minus 7, x goes to 1, is equal to -4. So this is just a shorthand way of saying, what does our output do? What is our output going as our input gets closer to 1? All right. So we're going to start adopting that notation so we don't have to write as much moving forward. So let's take another example, and I'm going to work through this example with you. We're going to look at how to use the numerical and graphical approach to find this limit. This function is a rational function, x squared plus 7x plus 10, divided by x squared minus x minus 6. And we want to find the limit of f of x, as our input x gets closer to -2. All right, so limit of f of x as x goes to 2. All right, so let's take a look at this. We're going to use the numerical version first and basically come up with some numbers. In this case, we're getting closer and closer to -2. So let me put -2 in the middle of some table. And let's get closer to that from below and from above. Now, weirdly enough, the from above is the -1.99, or maybe I do 1.999. From above is that way. Remember, from below is -2.1, -2.01, -2.001. So I started with a tenth away, then a hundredth away, then a thousandth away. And then I'm going to plug in to my function f of x. Now, this is going to take just a minute because there's a lot of calculations. I know you know how to do this, so I'm going to speed up that process here and just write in the numbers. So here we go. negative 2.1. When I plug that in, I get about negative 0.56866275. When I do negative 2.01, I get negative 0.596864, negative 2.001, negative 0.5996801. Now, if I plug in negative 1.9, I end up with negative 0.6326. Negative 1.99, plug that in. I end up with negative 0.6032064. Negative 1.999, plug that in. I get negative 0.6003201. So what it looks like is happening here is that as you approach both directions, it looks like the function is getting closer and closer and closer to a negative 0.6. Now, here's the interesting thing numerically about this function. If you were to take this function and you were to plug in negative 2, go ahead and do that for the top. The top would turn out to be 0, and the bottom would have also turned out to be 0. Now, this number, 0 divided by 0, is undefined. It's a really special thing. So we cannot calculate the actual output when x is negative 2. We can't calculate that. But in this case, we did find a limit. So that's what's happening in this scenario numerically. We get this weird 0 over 0, which again, we can't work with, but we can still find the limit. And the limit here is negative 0.6. Let's check this out graphically as well. So what I've done is I've graphed our function, our f of x equals x squared plus 7x plus 10 divided by x squared minus x minus 6. And you get this rational function right here. If we zoom in on what's happening at x is equal to negative 2, it really doesn't look like anything. So as you go x equals negative 2, it looks just like a normal function graphically. But what's really happening here at this negative 2, negative 0.6 point is there's actually a little hole in my function there, because the negative 2, negative 0.6 is undefined, or the function is undefined when x is negative 2. So you can't see that graphically because of the way your calculator or Desmos graphs this. It's really hard to see. But what's really going on is we have a point here where the graph kind of doesn't have anything. It has a hole in it, in other words. But you can clearly see that as the x values are approaching negative 2 from the left, like negative 2.1, negative 2.01, negative 2.0001, and as it's approaching negative 2 from the right, negative 1.9, negative 1.99, et cetera, and so it's approaching negative 2, negative 0.6, even though the graph itself has a hole there. And that's one of the big advantages of being able to deal with limits, is that even if there's holes in our graphs, or holes in our functions, we can actually come up with a number for the limit where we could not have actually plugged anything into the actual function and calculated where it's at. Okay. Now, these types of functions and these types of places where you plug in a number and you get 0 over 0 are kind of special. Whenever you have a 0 over 0, the mathematical concept that we have there is called an indeterminate form. It's basically when an algebraic expression has no value that you can calculate. All right. So we say it's indeterminate. I'm giving a very loose definition of indeterminate. I'm not being very precise, but the one that we're going to look at here is the 0 over 0 example. So 0 over 0, you should know, is an indeterminate form. There are others that we're going to see later on. So here's what I have. I have two functions that have an indeterminate form when you plug in the numbers. So we have a limit as x is going to 0 of sine 3x divided by x. If I plug in 0, I get 0 in the numerator and 0 in the denominator. And then I have a limit of h of x as x goes to -5. It turns out if you plug in -5 in the numerator, you end up with a 0. If you plug in -5 in the denominator, you also end up with 0. So I want you to use numerical and graphical methods to determine the limits that you see here. Go ahead and do those, and I'll show those in the next video.